continue our discussion in Chapter 6. And today we are going to focus on one of the variables in the equation for tau. That variable is Q. So I'm going to talk about shortly what it means, and then I'm going to talk about how we find it. And we're going to focus our discussion on the two types of cross sections that we have, which are rectangles and I-beams. So Q's would be found the same way, but would be significantly different for a different shape of a cross section. But we'll leave that to further discussion when you study further into mechanics of materials. All right. So let's start with the idea. We know that what we've been working toward in Chapter 6 is the idea that tau is different. Tau, shearing stress, is different at every point on a cross-section of a structural member, and also that tau tends to accumulate or to concentrate at discontinuities like fasteners or knot holes or whatever. But I gave you an equation that said tau at any point is equal to VQ over IT. And I also said that we're going to limit our discussion to cross-sections that are in the shape of an I-beam and cross-sections that are rectangular. So we know that V is the applied shearing stress. Shearing force. We know, or the responsive shearing force, depending on where, actually it's always a responsive, but it's in response to an applied, so there you go. Q, I've told you, is the first moment about the neutral axis, which we'll discuss in a moment. We've talked about I, or the moment of inertia, always about the neutral axis. We'll only deal with symmetrical I-beams, so we're always talking about this as our neutral axis. Rectangle by symmetry, neutral axis is right in the middle. So for a cross-section, whether you were looking for tau here, or here, V is going to be the same, I is going to be the same, and then thickness and Q sort of go together, but thickness is quite easy to find because basically what we're talking about for thickness is just, like at this point, would just be from here to here, the distance from here to here. But what is Q? Well, Q is the first moment of area away from the neutral axis, about the neutral axis. Right? So we're going to begin our discussion with a rectangle. For a rectangle, if we have a width of W and a height of H, we know that if we were, say we were interested in, let's just do, first of all, I'm going to start with what is the tau on the neutral axis, okay? Right on the neutral axis itself. All right, well, the answer to that is tau everywhere is VQ over IT. We would know V, we would know I, and T, the thickness, would just be this measurement, W. But what is Q? All right, Q is the first moment of area away from the neutral axis, about the neutral axis. So first of all, the formula for Q, which we'll just see now and we'll never use again, is equal to the integral of y dA. And because on each of these shapes, everything is a component of a rectangle, we can say that it's the summation of yi ai, which is quite a bit easier. But now, what the y is and what the a is are the questions that we have to answer in order to calculate Q. So let's look at Q for a point, we're just going to call this 1, on the neutral axis of a rectangular cross-section. Right. Well, there's only one piece, so we're not going to have to sum anything. But we need to find y and we need to find a. So q in this case is just equal to y times a. But what is y? Y is the distance between the centroid of the piece away from the neutral axis. And this word piece is where we get into trouble. We could think of it as a piece, or I sometimes refer to it as a chunk. All right? And then A is the area of the piece, or the chunk. So the question is then, that everybody would have at this point, what is the chunk? What in the world is she talking about? All right, so the answer to that is, we start by drawing a picture. You're given the point that you want to take the first, that you want to find shearing stress of. You want to find tau at this point. So what you do is you locate that point, and you locate its relationship to the neutral axis of the entire cross section. And in this case, those two pieces are coincident, aren't they? They're exactly the same. All right, that means that the chunk is this. In other words, I draw the neutral axis, I draw my point, and then I draw everything, I shade or consider everything away from the neutral axis of that point. Now, similarly here, I'm going to do this one in just a moment, but to show it, I would draw, if I wanted the shearing stress here, I would draw a line through that point, and then the chunk is everything away from the neutral axis, above that point. Now, if the point were right here, I would draw a line through it, and then I would locate the neutral axis. I would locate the line that's parallel to it, or perpendicular in cases, above that point, and the chunk would be everything below it. But you see what I mean by away? It doesn't matter if it's above or below, or even if it's side to side, which we'll talk about with I-beams in just a moment, but it's always away from the neutral axis. So the way to find the chunk is to find the neutral axis, find the point, draw a line through the point, and decide what piece is away from the neutral axis.
So the chunk's the difference from it, not the actual inset.
That is correct. It's the piece of the cross section that is the furthest away from the neutral axis. It can be in the y or the x direction, which we'll talk about in a minute. Y is always up and down, but the chunk can be either, like for example, let me draw this.
Just if you do the y and x, you could like, even when they do cross parts, like you can throw away all of that.
Well, for finding Q, yes. Like if we wanted to find the stress right here, the shearing stress right here on this I-beam, we would draw that line, okay, like this. The chunk is going to be over here.
But since it's off of its axis as well, wouldn't it have its x component on its chunk?
No, the reason for that is because tau is not an x or a y phenomena. Tau is over a surface. And so that's an excellent question. And that was actually before you came in. I was looking that up to see if I could make that generalization, because I thought, you know, that always works, but is it valid to state that? Mm-hmm. And the answer is yes. So, an awfully good question. All right, so the first thing we do is find this chunk. So we're going to start with this picture right here. This is the one we're going to work with first. All right? So what is y? Y is the distance between the centroid of the chunk away from the neutral axis. Well, if the height of my rectangle is h, what is the height of my chunk in this case? The neutral axis is in the middle. So wouldn't the height of the chunk be h over 2 from here to here? Yes? Are you feeling it? No? Okay. So since this is a rectangle, now I need to find the distance between my neutral axis and the centroid of the chunk.
Wait.
Mm-hmm.
So you just split that in half and just put the point, and they're doing the same?
That is correct.
So
by symmetry.
Okay. So you can pick either one to throw away?
No, it has to be away from.
But
Oh, I'm looking for, like, could I do this half?
Yeah.
Absolutely. It's
Okay.
gonna come out to be, that's a great question. It's exactly the same.
Okay.
It's exactly the same. Very, very good question. Okay. But I'm trying to make this, and that's a very good thing to think about. If you're on the neutral axis, they are going to be exactly the same. It could be this or this. Here, it's only going to be this. It would never be this,
yeah.
because that would include the neutral axis, and you just want to go away from the neutral axis, okay? Not toward the neutral axis, okay. So anyway, so then we know that this chunk is going to be h over 2. So that means if I look at the area, my area in this case is going to be the width, w, times the height of the chunk, which is h over 2, right? Well, what is my y? My y is the distance from the centroid of the chunk to the neutral axis. By symmetry, the centroid of the chunk is right in the middle, which is at what? What's this distance? It's half of h over 2, which is h over 4. So that means that my y times a for this is going to be width times height over 2 times height over 4, which is h squared w over 8. Okay. Now, for this chunk, and I guess you can use the word piece. I just prefer chunk because that's what it looks like to me. It's just a chunk of stuff, okay? Let's do the same thing here. We've identified we want to find tau here. We've identified, let's say, that this distance is h over 2. Excuse me, h over 4. We're halfway up. So this is h, that's h over 4. My centroid then is going to be h over 8 from the top. But what is it from here? It's h over 2, or h over 4 plus h over 8, or 3h over 8 is my y. It's always the hardest part. And my area of this chunk is h over 4 times w. So that means for this chunk, the q is 3h over 8 times h over 4 times w, which is 3h squared w over 8 times 4, which is 32. Okay. And if you drew this point right here, it would actually be the same because this distance would still be 3/8 of h, right? So you're always looking at the distance. The y is always the y distance from the centroid of the chunk to the neutral axis. And if your math leads you to find it from the edge, then you have to subtract it from the distance from the edge to the neutral axis.
So
Yes.
I guess my only question left on this is, if you have a point that is both offset in the x and y direction, and you have to pick one of them, which one do you pick?
No, that's another good question. It's a great question. It's actually like one of the central questions of this. So let's look at this chunk. Or let's just say that you had a point here, right? And you were looking at this point. It's exactly the same because the shearing force acts on a plane, so it acts over the whole plane at the same time. So it's going to be the same as long as you've got the same dimension in the x.
Yeah.
You're still talking about y bar, and you're talking about a away from the neutral axis. So it's exactly the same.
So if we had that I-beam right there,
Yep.
where it's off in both parts,
Yes.
then which
Mhm.
do you take the flip of the x or do you take the flip of the y?
No, the y bar is always in the y direction. So you find this chunk, you draw a line through its centroid, and there's your y value right there.
So you actually just took that chunk because it's doing both. There's just a gap.
Exactly.
Oh,
That's exactly right.
okay.
And then this is your width, and this is your height. So the area is width times height, and your y bar is that dimension.
Got it.
Yeah, it's a good question. So, and as I said, these are the only two shapes that we're going to deal with. Now, the difference becomes, let's look at an I-beam. And let's say, I'm going to run through this. Actually, I'm going to do just what I did, only I'm going to do it in a methodical way. Let's say that we want to find Q of this point. All right? So the first thing is we identify where the neutral axis is of the I-beam, which is right in the middle, because that's the only kind of I-beam we're going to use, is symmetrical from top to bottom. And then we think about away from the neutral axis. Okay, so I can kind of think about this. This is called the idea of shear flow, that shear flows over the surface. So I can say, what's away? Well, away is like this. I turn a corner, and since it's planar, I just draw a line like this. So my chunk looks like this, right? So that means that my A is this width of the flange right here, and the height of the flange. So it's width times height. But what is my Y? My Y is the distance from the midpoint of this chunk about the neutral axis. The neutral axis is in the X direction. That means that Y is always Y. In other words, I don't go from here to here. That's an X direction. I always go in the Y direction. So this is going to be, if this was capital H, the height of the whole I-beam, this would be half of H. And this little chunk right here, my centroid here, is half of little h. So my Y bar is going to be half of big H minus half of little h. And so my Q is just WH times 1/2 big H minus 1/2 little h. Okay. Now the only other one I want to show you definitely is, what if we take an I-beam, because once again, just rectangles and I-beams, this never becomes an issue with the rectangle. But if our cross-section is rectangular, I'm going to put a couple of numbers in this one because it gets a little bit more confusing, so I want to get out of a symbolic, literal talk. I want to get to just some numbers. So let's say that my dimensions are 3 inches, 1 inch, 3 inches, 1 inch, and let's say let's call this 6 inches total, and the width here 2 inches. Okay. I'm also using different numbers. I mean, this looks more like 1 inch, but I'm using different numbers because when we do the calculations, I don't want you to think she's talking about the width of the web or she's talking about the height of the flange. So I'm using different numbers so you can see that. And let's say that we wish to find Q about a point right here that is 1 inch, or let's say 1/2 inch to keep my thing going, below the intersection of web and flange. Okay, well the deal is that to do this we have to look at 2 chunks because we don't really have a facility for finding Q of something irregular like this. But what we have is we want to find Q of this, we'll call that Q of 1, and then we want to find Q of this, which is Q of 2, and add them together, and that will be Q for our equation. All right? So how about 1? First thing is we need to find the neutral axis, which if this entire thing is 6 inches, my neutral axis is at 3 inches from the bottom, or 3 inches from the top. Let's look at this. If this is 1 inch, this top flange, that means that my neutral axis of that is 1/2 inch from the top, or 2.5 inches from the neutral axis. So the distance from here to here is 2.5 inches. So Q1 is the area of that upper thing, Q2, A2 times Y2. That's what I'm trying to say. So my A2 is 3 inches times 1 inch, and my Y2 is 2.5 inches. So my Q of part 1 is 3 times 2.5, which is 7.5 inches to the 3rd power. And inches to the 3rd power is the appropriate unit for Q. All right, now let's do this chunk right here. This is 1/2 inch. This is 2 inches. So we know that this is equal to A1, Y1. A1 is 1/2 inch times 2 inches. And now we need to go through that bugaboo of finding the distance from the neutral axis of this little bitty chunk to this neutral axis. We know that this entire distance is 3 inches. And since this is 1 inch wide, we know that the distance from here to here is 2 inches. We also know that this is a 1/2 inch, which means its centroid is right at the middle, or 1/4 inch down. So that means that we are 2 inches minus 1/4 inch, which is 1 3/4 inches. So this is 1 3/4 inches. So if I multiply that, 1/2 times 2 is just 1. So A1, Y1 is 1 3/4 inches to the third. And my Q of that composite shape is then 7 1/2 plus 1 3/4, which is 7, 8, 9 1/4 inches to the third. And that is the value that you would use in the equation. All right. Do you have any questions for me?
So the I-beams, like, you're just using the I-beam as reference because block is just a simple
Yes. The only 2 geometric shapes I'm going to use in this chapter are the rectangles or the I-beams. Absolutely. And if you have a different structure, you have to go through this with a different configuration, which is not hard, it's confusing. So like if you had a structural member that was in the design of a circle, you have to find the neutral axis, then you would have to take this chunk, then you'd have to find the neutral axis or the centroid of that chunk, and then you'd have to do the same thing and find the area of the chunk and the y bar of the chunk. When you get into other shapes, like if it's more complicated, doing the integral form, YDA, integral of YDA, is a little bit easier, but we're not going to do any of that stuff. All we're going to do are rectangles and I-beams.
Are you going to make us do this with the rebar that we put to the...
No! No, we won't do it with rebar, I promise. Just cross sections. So just basic, normal, non-transformed cross sections in the shape of an I-beam or the shape of a rectangle. All right, do you guys have any questions for me at this point? What I would like to do, since I'm going to just give you a little homework assignment today to get practice on, but we know that tau is equal to VQ over IT, and I'm going to ask you to find a couple of the components of these. Now, you're welcome to go ahead and find tau if you want, but basically I want you to determine what would be V, what would be Q, what would be I, and what would be T on a couple of different shapes. So 6.38, there are 2 points, A and B, and this is an I-beam. So you'll be able to do pretty much the stuff that we just did in class. And and then we get into what Dane was asking about, some transform sections, which I'm not going to ask you to do. See? Excuse me again. But I would like to have a rectangle, and it's not. 6.1 is a really interesting question. But all I really want you to do, this is a rectangle, but it's 3 boards that are nailed together. So we don't really pick a point per se, but what we do is we have nails going through, and this is a plank. So we're looking at this surface. So my chunk is this, and my other chunk is this below. So in other words, 6.1, you can come up with the same ideas, but where the chunk is not determined by this arbitrary asking of I want you to find it at this point. It's like this is where the nail is, so that's where it's going to happen. Okay? 6.1 also asks you a little bit about something called shear flow or shear per nail. I'm not asking you to do that. I just want you to find V, Q, I. You don't even have to find thickness really, but if you wanted to, you could. All right? Do you guys have any questions? All right, so we have our first homework, and you're so excited. All right, but the good news is we put together all the pieces. Doing the homework, finding tau at this time is going to be easier. It's getting those pieces, and so that's why I really wanted to lay out a really methodical way for you to find Q and I, and then to define what types of problems you're going to be responsible for. So, all right, well, gentlemen, have a lovely afternoon and a great weekend. I'll post this stuff up, and we'll see you Monday for more fun with mechanics and materials.